Good morning, students. So in the last two classes, we are discussing about time independent perturbation theory, in which we applied some techniques to find out the energy corrections for non-degenerate cases and degenerate cases. And especially in the non-degenerate cases, we could obtain the expectation value of the perturbation field. And in the last class, so this is about a degenerate case, we diagonalized the matrix. We could obtain some simultaneous equations. We converted into secular equation, and thereby we got some determinant of the matrix. We converted into matrix, and we could apply in the roots. Those roots will give us eigenvalues. So these eigenvalues will be the corrected energies for the degenerate case. So in the non-degenerate case, for each wave function we will have each energy, whereas in the degenerate case there will be many wave functions, we will have only one single energy, and the perturbation which we are going to apply will remove the degeneracy. So this is what in the last class we discussed. Either it can remove fully or it can remove partially. The example that we can go for the former case will be Zeeman effect. Zeeman effect is nothing but splitting of spectral line, its own components in the presence of magnetic field. So this is a very, very famous example for removal of degeneracy fully. That is the moment when you are going to apply the perturbation, the degeneracy will be removed fully, completely. Whereas in the today's class, in Stark effect, so this will be removed, the degeneracy will be removed partially. That is, still it will have degenerate values as well non-degenerate values, so which we are going to see at the end. So this is a very, very, very famous example for partial removal of degeneracy, Stark effect. Okay, we are going to look into. So Stark effect mainly says that we have a spectral line that will be split into many components in the presence of electric field. So this will happen symmetrically, what we call this as linear effect. So linear effect in the sense, the spacing between spectral lines will split into equally. The moment when you are going to switch off, again it will come to original position equally. Suppose when you are going to increase the electric field, again the spacing will increase evenly. So this is for linear effect. And another one is for non-linear effect. So there are two types, linear effect and non-linear effect. Non-linear effect usually we will call this as quadratic effect. Okay. So we'll discuss about the Stark effect today. The perturbation of the system in the presence of uniform electric field. So we are going to apply uniform electric field. The splitting of spectral lines into components in the presence of electric field is nothing but your Stark effect. The splitting of energy levels is known as perturbation. We are going to take the example of hydrogen atom. That is, light interacts with the hydrogen atom. The electric field interacts with the hydrogen atom. The hydrogen atom is spherically symmetric because the potential energy that we are going to consider as spherically symmetric. The expression for spherically symmetric will be V of r vector equals V of r. The amount of splitting is nothing but Stark shift. Okay, Stark shift. Now, as I said, the atom is subjected with the electric field. Okay, so there will be an interaction between these two systems. So interaction energy, it happens that the electric moment of the atom with the electric field, that will happen. So interaction is nothing but the electric moment of the atom with the electric field. So of hydrogen atom in the presence of electric field is given by this expression, AF plus BF squared plus CF cube. Here we are denoting electric field as F, but usually we will take electric field as E in other subjects, other classes. But often we will be getting the energy eigenvalue which is referred as E. So that's why we have kept F as the electric field. Okay, and here A, B, C are constants. You look at the first term says about AF. Suppose in the absence of other terms, the first term refers AF. AF is a linear effect. Okay, And if you include the other terms, that will give us non-linear effect. So what we call this as quadratic effect. And of course it depends on the electric field strength also. It depends on the electric field strength. Suppose if electric field strength is say less than 10 power 5 volt per centimeter, then the effect is nothing but linear effect. So what we call this as first order Stark effect. So that will be linear, depends on the electric field strength. If it is more than 10 power 5 volt per centimeter, more than 10, so we'll have to include the other terms, then we call this as quadratic Stark effect. Okay, the second order Stark effect is quadratic. Okay. Now the Zeeman effect was found by Peter Zeeman in the year 1896. So just after 17 years, Jones and Stark found out this effect in the presence of electric field, splitting of spectral lines in the year 1913. Because see such a long, just 17, it took 17 years nearly, because at the time we had to go with a high potential. So people did not find out the high potential voltage. So that's the reason that it took long years to find out this effect. Okay, so Stark effect was discovered by Jonas and Stark in the year 1913. So he could obtain the Balmer series of hydrogen atom were split into number of symmetrically spaced components. So as I said, linear effect means the spacing of the lines will be always same on either side. Even if you switch it off, it will come into the original position. If you are going to increase the field, it will increase evenly. So that's called a linear one. So this is symmetrically spaced components. Okay. So he has used the second one. Of course, we know the spectral lines of hydrogen atom, Lymer, Balmer, Paschen, bracket, Pons, and all those things. And he has used the second one, n equals 2. It means that from higher energy levels, the lines will come into the n equals 2. Okay. And suppose you are going to apply the electric field in this direction, you are going to observe. So you have an atom like this, you are going to observe the electric field in both the ways, transverse view as well, longitudinal view. So transverse view says that the spectral lines will be always plane polarized, and some components will be parallel to the electric field. We call this as pi components. And some will be perpendicular to electric field. We call this as sigma components. So they are all linearly polarized. Suppose if you are going to view in longitudinal view, then we will obtain only sigma components of spectral lines. This will be unpolarized. So as I said, the components lie symmetrical on both the sides of the original line. Okay. So we discussed already the first order Stark effect will be linear, and we will have to apply the electric field below 10 power 5 volt per centimeter. If it is more than 10 power 5 volt per centimeter, we go with this one as a second order quadratic effect. Okay, non-linear. So he got the Nobel Prize in the year 1919 for the discovery of Doppler effect in canal rays and the splitting of spectral lines in the electric field. Okay. He observed this Stark effect, and he has used Balmer series. Balmer series lines of hydrogen atom, and with a high resolution spectrometer. And of course, suppose if you look into any spectral line with a low resolution spectrometer, we could see only a single line. If you use high resolution spectrometer, that line will consist of many lines. What we call this as fine structures. Similarly, when you look at the stars and with the help of some poor resolution telescope, we look into star, one single star. If you look at with the help of high resolution telescopes, then those stars will have binary stars. 2 stars will be there. So something like that. The first quantum mechanical treatment was done by Pauli using matrix mechanics for a Weisenberg idea. And Staudinger in the year 1926, he also wrote a paper on Stark effect, maybe third paper on quantum theory, in which he introduced his perturbation theory. Okay, the spacing between the sublevels increase linearly with the applied electric field. So this is about the Balmer series. So Balmer series is a visible region on the lines which are coming out from many levels to n equals 2. So there are few lines, H alpha line, H beta line, H gamma line, H delta line. So they are all fine structure views for different wavelengths. and in fact this H alpha, number of components for H alpha will be very less, and this will have more and H delta will have more number of components. Okay, so the Stark effect will be observed perfectly here. So what are the applications of Stark effect? This is mainly there are 3 applications, and this is about highly precise atomic clocks are used in various industrial applications, including GPS system, global positioning system, and telecommunications. The Stark effect can be a source of systematic error in these clocks, and its precise understanding and correction are essential for maintaining accurate timekeeping. Okay, the last one is very important, which we study in the research level. In addition, the industrial spectroscopy, the Stark effect can be used to study the interactions between the atoms and molecules and electric fields. In fact, we can study the structure of the atom and molecules using this Stark effect. Okay. So this is a theory that it begins the Stark effect in hydrogen atom. So as I said, we have a spectral line. So this will be split into its own components in the presence of electric field. It's nothing but your Stark effect. So perturbation is nothing but electric field. So your total Hamiltonian will be unperturbed Hamiltonian plus perturbed Hamiltonian. This perturbed term has come because of application of the electric field. Okay. Now we are going to apply the external electric field F, which is along the Z axis. Okay, that is very important. And your H naught will be unperturbed Hamiltonian, which is given by the addition of kinetic energy and potential energy. Here we have used, instead of M, we have used reduced mass. Okay, ME and MP. So your mu will be ME MP divided by ME plus MP. So we know already this. What are these R? Usually we will consider this R as a mean distance between electron and proton. Here we have used your reduced mass. So the R will be the distance between center of mass and center of point. So your R. Suppose if we have used only for the hydrogen atom, this model is for hydrogen atom. So we have considered Z as, here Z should be there, so Z as 1. If it is more than 1 electron, we can consider as Z. Okay. Where H prime is a perturbed term due to electric field, applications of electric field. So H prime equals, we have just now we discussed about F is in the direction of Z. So EF is Z. Okay. EF is Z, which is equal to EF, and we are going to use spherical polar coordinates. So Z will be your R cos theta. So here E is the electron charge and Z equals R cos theta in polar coordinates, we know already. Okay. Now, very important thing about the interaction of energy with the atom. Okay, that is very important. Suppose we consider this is an atom, hydrogen atom, and this is your nucleus, proton is there. Okay, and surrounded by electrons, we go with the electron cloud now. We are going to apply the electric field in the Z direction. So your positive terminal is here, negative terminal is here. The atom is subjected in the electric field. Okay, the moment when you are going to so you just consider this is an atom and nucleus is at the center. We have the electrons around the nucleus, correct? So you are going to consider this electron as an electron cloud. So in the presence of electric field. Now the moment when you are going to switch on the electric field, all the electrons will be attracted towards the positive terminal, positive potential. This proton will be attracted towards a negative potential. So there will be a stretching, okay, between positive and negative. This stretching, in the sense, what we call this as induced polarization. That is, charges are separated. You have protons, positive charges are this side, you have negative charges are this side. What we call this as induced polarization. Okay, so this stretching is nothing but induced polarization. This induced polarization will cause us the dipole moment of the atom, dipole moment of the electron. So you have a positive charge and negative charge, which is separated by the distance r, and this will happen. The r distance will be away from it. Okay, r goes outside. But what of the direction? The direction always will take from negative to positive. So that's why we have termed as minus n here. So this is the expression for your dipole moment. Dipole moment always will be given as modulus charge multiplied by its distance. Here the distance is negative sign because it goes from negative to positive. We will have to always take negative to positive. So P equals minus ER. Okay. We have taken the expression for your potential energy. Potential energy in the sense, suppose if we consider this is a stretched one. So you have a positive charge here and you have a negative charge, and you just consider this is a dipole moment. Now you are going to apply the electric field in this direction. Okay, the moment when you are going to switch on, what will happen? This dipole moment will have either, this will rotate like this. So this will have potential energy. Okay, the dipole moment in the presence of electric field acquires an additional energy. So this will have additional energy. This additional energy is nothing but your perturbing Hamiltonian. So your potential energy is given by minus P dot F. Just to substitute here the Hamiltonian, which is nothing but your minus P dot F. This additional energy is nothing but your perturbing Hamiltonian. So your H prime equals minus P dot F, and the expression for P will be your minus E dot R. So that will give you plus ER dot F Z. Okay. Look at the left hand side. This is an operator. So perturbing Hamiltonian is an operator, and similarly there must be an operator on the right hand side, which is nothing but your eject cap, position operator. So that's why it is termed as H prime equal to E of Z. Of course, your R vector and Z cap will U Z. So that's why H prime equals E of Z. Okay. So in the earlier side, we have written H prime equal to E of Z. So this is the explanation for your the perturbing Hamiltonian, which is equal to E of Z. For hydrogen atom, the potential energy and wave functions are spherically symmetric and has the same form for all orientations of the polar axis. Therefore, there is no degeneracy. Okay. The wave function, we know already this discussion. The wave function for any spherical symmetric potential is expressed in terms of spherical harmonics. So we have already studied in hydrogen atom itself. So if we consider any spherical symmetry, then we will have to go only with the spherical polar coordinates. Okay, the wave function will be in terms of spherical polar coordinates, which is the product of radial part and spherical harmonics, we know already. And in addition to that, it has even parity when L is even. So parity, the term that we already studied earlier in the last unit. So symmetry. Okay, this is parity. It's a symmetry operator. Inversion, correct? Space inversion. So it has even parity when L is even and R parity when L is odd. And this parity depends only on the spherical harmonics, not on the radial part. So which we will see now. Okay. So now the wave function labeled by NLM. So this wave function labeled by NLM. N stands for principal quantum number. L goes for orbital quantum number. M is nothing but magnetic quantum number. So it is labeled by NLM. So which is a function of R theta phi, which is equal to the product of radial part and angular parts, spherical harmonics. So what we call this as spherical harmonics. So this is your polar angle and this will be your azimuthal angle. R stands for radial part. Okay, radial distance. The connection between all the three, that will be given by this one. Look at here. L goes from 0, 1 to up to n minus 1. Okay, the connection between L and M will be minus L to plus L through 0. Okay, suppose for example, if you consider n equals 2 or n equals 1. For example, we will go with n equals 1. What is the value of L? L for n equals 1, L will be 0 because this is 1 minus 1. Okay, L will be 0. Okay, if L equal to 0, M will be 0 again. For n equals 1, L will be 0, your M also will be 0, ground state energy. N equals 1, L equals 0, M also will be equal to 0. Suppose we go for first excited state, n equals 2. So your L will be very good, 2 minus 1, so 1. What about M? M will be minus L2 plus L through 0, we said. So minus 1, 0, plus 1. 3 numbers. Is it okay? So this is the way that we usually will calculate. Now for the unperturbed eigenenergy for the hydrogen atom, we studied already for the ground state, which is given by this expression minus 13.6 divided by n squared electron volt. So your minus sign stands for the binding energy, which binds with the nucleus. So minus 13.6 divided by n squared. Suppose for the ground state, just now we discussed about with the quantum numbers, n equals 1. So this will be minus 13.6. And what about your wave function labels, NLM, that will be 100. Is it okay? Your 100 will give you minus 13.6 electron volt. Okay. Whatever may be the combination, you will get the same energy. 100, you will have the another combination that also will be 100 only. So whatever may be the combination, you will have minus 13.6. It means non-degenerate. For only one wave function, we will have a single energy. We will have minus 13.6 electron volt. That's all. Okay. If you go for n equals, now n equals 2 here. So your L value will be 1. M value will be minus 1, 0, plus 1. So now we can go with lot of combinations, correct? We can go with lot of combinations with NLM. What are the energy for n equals 2? The energy will be minus 13.6 divided by 4. So that will be minus 3.4 electron volt. Same energy. Okay, for all the 4 or 5 wave functions, we will have the same energy. So what we call this as degenerate. Different combinations of NLM. See, you have when n equals 2, L equals, you will have L equals 1 and M will have minus 1, 0, 1. We can have different possibilities of NLM, different combinations of NLM. What is the energy? Energy is the same. Okay, energy is the same. So this one. So that's why we will always go for with, we will have to add with some correction, that energy. So this is for the unperturbed, this is for the perturbed energy. Okay, we'll look into in detail. So first order correction in the ground state energy. So as I said, here for the ground state, n equals 1, L equal to 0, M equal to 0 for the ground state wave function. Okay, labels. Since the wave function is spherically symmetric, having the same form for all the orientations, V of r vector equal to V of r, and there is no degenerate. Okay, we know already. So for the ground state wave function, we already studied this one for the non-degenerate case. Can you remember? For the non-degenerate case, the expectation value of the perturbing field is given as an expression for the non-degenerate case. This is for the non-degenerate case. Can you remember? Okay. So H sandwiched between your NLM. So N stands for 1, L stands for 0 here, M is nothing but your 0. So get 100 with draw 100. For n equals 1, L equals 0, M equals 0. So we know the wave function earlier we studied in hydrogen atom itself. The wave function is given by radial part. Wave function is given by this equation. Correct? We have already studied this one. Okay. Now you just we will calculate now. We will calculate. Okay, En1. We are going to calculate now. So in we will have to use the polar coordinates. So we will have to have 3 limits. This is for the radial part, and this is for the theta part, and this is for the phi part. So H sandwiched between your normal wave function and its complex conjugate. This is written in terms of matrix method. This is written in terms of wave mechanics. Both are the same. So we are going to integrate. We are going to get the value, eigenvalue. Is it okay? Both are the same. See, this is a wave function, and this will be a normal wave function. H is MR here. The expectation value is given by this expression, equation 4.55. Is it okay? Your H prime equals EFZ, which is nothing but EFR cos theta. You substitute here, EFR cos theta. EF is constant, I can pull it out. EF is constant, I can pull it out. Okay, I can pull it out, EF. Then I can substitute your wave function. The expression for wave function is given by this one. The complex conjugate of this one also will be the same thing. There is no I here. Okay, the complex conjugate. So substitute here. So we are going to substitute. So this is the expression for your psi star. This is the expression for your psi. Okay, this is the expression for your psi. This will be your perturbing field Hamiltonian. Okay, come on. This one is this one, and again the same thing. And Hamiltonian will be your EF or cos theta. You pull EF out. Okay, this multiplied by this first radial part, that will give my pi a naught cube. Okay, and you have r is here, and you have r and r squared, so that will give us r cube. E power r multiplied by this one, that will give me e power minus 2r by a naught. So r part alone, radial part alone, I have taken out. What of theta part? You have cos theta part is here, sin theta, d theta. So cos theta, sin theta, d theta. The remaining term will be your azimuthal angle d phi. So we have separated now radial part, angular parts. Is it okay? Equation 4.58. Any doubt? Now I am going to multiply and divide by 2 here. Okay, so multiply and divide by 2, that will give me 1 by 2, 2 sin theta cos theta. 2 sin theta cos theta is nothing but sin 2 theta d theta. Okay, so now I am going to integrate this equation separately. Okay, radial part separately, angular part separately. Of course, we know the answer for this we have already studied. This one will be 2 pi. Okay, we know already this. Only we are going to integrate separately these two expressions. One is for radial part, another one is polar angle part. Is it okay? Now we can solve 2 or 3 methods. We will solve 2 or 3 methods. We will get the answer, and whichever method is easier you can follow. Okay, first we will solve with the ordinary integration. That is, we are going to take this first expression, r cube e power minus 2r by a naught dr. You keep 2r by a naught as x. Okay, then 2r will be x a naught. Then your r will be x by 2 a naught. We need to have r cube, correct? So just cube, that will give you r to the power 3, which is equal to x to the power 3 by 8 a naught cube. What of dr? Your dr will be a naught by 2 dx, correct? You just differentiate. So your dr will be a naught by 2 dx. So we have to substitute for dr. So that's why we have differentiate with respect to that dr equals a naught by 2 dx. Okay. Now r cube. What is r cube? X cube by 8 a naught cube. What is dr? A naught by 2 dx. So 8 multiplied by 2 will give me 16. A naught cube multiplied by a naught will give me a naught to the power 4. Your r cube will be your x cube, and this term as e power minus x dx, correct? This expression is okay? Radial part, we have simplified from 0 to infinity. And what of this expression, that will give us gamma integral, which we have already studied in mathematical physics. So this expression for this one, the solution of this one will be gamma 4. Gamma 4. What is the gamma 4? Gamma n equals n minus 1 factorial. So gamma 4 is nothing but 3 factorial. Again, which we studied in MP, mathematical physics. So the answer for this one, first integral will be a naught to the power 4 divided by 16, 3 factorial, which is nothing but 3 multiplied by 2, that will be 6 divided by 16, which is equal to 3 by 8 a naught to the power 4. So we have finished the first solution for the radial part. Any doubt? Any doubt? Okay. Now we will go for the polar part, second one. Second one also we can have different methods. We'll go with different methods. What are the method that is easier for you, you just take. Okay. So 1 by 2 sin 2 theta. So sin 2 theta you can integrate, that will give you answer as minus cos 2 theta, correct? So 0 to pi. So remove the minus sign, I am going to change the limits. So that will give you cos 2 theta pi to 0. Cos, substitute the limits, cos 0 minus cos 2 pi. Cos 0 is 1, cos 2 pi also 1. So 1 minus 1, answer is 0. Simple one. So the answer for the second integral is 0. Another method for second integral, which we will be using later for different problems, that's why I am going to discuss now. So 0 to pi sin theta, correct? This one. So this is one method. Okay. This is another method which we are going to see now. So that will be easier for you for your assignment problems. So that will be cos theta sin theta d theta. So this sin theta can be written as d cos theta. Okay. I am going to keep this cos theta as u. Cos theta as u. So you have kept cos theta as u, then you will have to change the limits also. Okay, when theta equal to 0, your u will be 1. Okay, when theta equal to 0, cos 0 is 1, so u will be 1. When theta equals pi, cos pi is minus 1, so u will be minus 1. So limit will be changed to minus 1 to plus 1, correct? Limit will change into 1 to minus 1. 1 to minus 1. Okay, cos 0 is 1, so 1 to minus 1. And sin theta d theta, which is sin theta d theta, which is nothing but minus du. So that's why this minus is there. So minus u du. Is it clear? Is it okay? So I will change the limit now, removing the minus sign. So minus 1 to plus 1, u du, u squared by 2, minus 1 to plus 1. So 1 by 2, 1 by 2, yeah, you will have minus 1 by 2, answer will be 0. Okay, second term answer is 0. So we have calculated the radial part, we have calculated this one, and we have calculated this one also, putting together. So this is the answer for the radial part, answer for the polar part, answer for the azimuthal part. The answer is 0. So it implies that there is no first order correction. So this is equal to 0. Okay, there is no first order correction. First order correction, there is no first order linear effect. So there is no linear effect for the Stark effect. Okay, there is no first order correction. It implies that. And this is the simplest method. Instead of solving, integrating all those things, we are going to solve another method. What we call this a symmetry operation method using parity operator. Very simple one. So instead of going for all the tedious equations, so you can go with simpler ideas. This is about parity. Parity is mirror symmetry, which we studied already. This is space inversion operator. Okay, parity operator. So we know about parity operator. The eigenvalue of parity operator is given by this expression, and it depends only on spherical harmonics. Look over there. So eigenvalue of the equation is given by this one. So this is your eigenvalue and depends only on L. Very important one. So parity operator depends only on L. Okay. When L is even, it has a even parity. When L is odd, this must be odd parity. So you have to remember those things. So this will work out only for the spherically symmetric. V of r vector equal to V of r. So those things are very important. Now taking into the point. Now the definition for your parity operator is given by this expression. Look at this expression. The effect of parity operator does not change the radial part. See, r becomes r itself. What of theta? Theta becomes pi minus theta. So when you are going to apply the parity operator for the system, the theta becomes pi minus theta. Phi becomes pi plus pi. So whenever you see theta, you have to substitute pi minus theta. Or let it be like this. So it doesn't change with r. R because of this potential symmetry. V of r vector equal to V of r. So r will not change. The effect of parity operator on r is as it is. There will be no change in r. Whereas theta becomes pi minus theta and phi becomes pi plus pi. Okay, you will have to remember. Now we just go with the same thing. We know already the first order correction. Okay, go with the same thing, first order correction. And we know this expression. Okay, we know we are going to solve this one. Come on, it's very simple one. Solve this one. Okay, we are going to solve. We have substituted E of Z is nothing but r cos theta. We have pulled E f out. Okay, this is another method. This is your wave function. This is another wave function. And r cos theta is nothing but a multiplicative factor. It is not a operator. So I can pull it out. If it is an operator, you can't change. Okay, so it's just a multiplicative factor. So I can pull it out, and this thing will give me mod of psi square. Is it okay? Half an hour. So r cos theta is a multiplicative factor. So if it is so, it is not an operator. It is not an operator. So if it is so, we can pull it out. And these two things that will give us mod psi square. Now the parity operators we are going to operate. Okay. Now you substitute for theta, just substitute pi minus theta. So cos theta is replaced as cos pi minus theta. So which is nothing but minus cos theta. Okay, cos pi minus theta that will fall into second quadrant, ASTC. For sine alone, we will have negative values. So cos will have negative values and tan also will have negative values. So we will have minus cos theta. Okay. So we know already Z equals R cos theta. And operator P is at the answer that we have obtained as minus cos theta, it becomes minus Z. Correct? So which is nothing but your odd parity. If operator operates on Z will give you simply Z, it is even parity. It is minus Z. So it is nothing but odd parity. So odd parity. So this is your odd parity. Is it okay? Now we will go for this wave function. If wave function is odd, the square of the wave function will be always even. Even if the wave function is even, the square also will be even. Odd and even, the square mod square, that will also be even. So this wave function will be even parity. Odd parity multiplied by even parity will be always odd parity. Integration of odd parity will be always 0. That's all. The answer is 0. So earlier we obtained all the difficult integration, we obtained answer is 0. If you are able to understand this concept, the answer will be very simple. You can write in this exam. Okay, you can write the exam. Very simple. So integration of odd parity will be always 0. Integration of even parity will have some answer. Okay, so integration of odd parity will be 0. So thus in the ground state of hydrogen atom, there is no first order Stark effect. So this answer is 0. The expectation value of the first order Hamiltonian is 0. So it implies that there is no first order correction. Okay, there is no first order Stark effect. Is it okay? Any doubt?